Hey there, it's Shannon MATHCHICK Myers, and today we're continuing our exploration of series and convergence. This is part 2 so far. We had a warm-up which developed a lot of ideas, so make sure that you check out that warm-up video. So, convergent and divergent series. First definition, for the infinite series, summation from n is 1 to infinity of that sequence inside a sub n, the nth partial sum is the summation from I equals 1 to n of a sub I, which would be a1 plus a2 plus ... plus a sub n. And that's also denoted as capital S sub n, nth partial sum. If the sequence of partial sums, assuming that this is ordered, okay, we're ordered a sequence of partial sums in an ordered fashion, converges to sum S, then the series, summation n equals 1 to infinity of a sub n, converges. The limit S is called the sum of the series. And so S would be a1 plus a2 plus ... plus a sub n plus ... And then as a summation, that would look like the summation from n. We now put n into as the index of the summation, since it's going to infinity of a sub n. The first summation had n as the final value you plug in for I in the series, which is why we had to change the index to I. But for this one, we're going to infinity, so we can keep that index as n. So if this sequence of partial sums diverges, then the series diverges. Okay, so let's take a look at what we were looking at in our warm-up. So our warm-up, we had we basically kind of derived the geometric starting at 1, what that infinite sum would be. And so this is the expression that we found. So if we take a look at our calculator, and you make sure you're in sequence mode, then you can actually, since we found what this sum was, we can't always do that, right, as in a formula. And so our nth partial sum for this one is as above, right? So now I'm going to go ahead and enter this in so we can see, hey, does this converge or not? So we've got parentheses 2 raised to the... Now this thing that looks like an n here is called eta in Greek. And then this is minus 1 into parentheses divided by 2 raised to eta. And then let's make a graph of this. And it's really pretty cool, right? As you go on and x gets larger and larger and larger, right? You can see that we're converging to a specific value, right? A specific sum. So here and the thing that's beautiful about this is the sequence of partial sums. So this is, something that is not, let me take a capture of it. This is something that is a sequence of partial sums for our series. Excellent. And then copy to photos. All right, so basically what we have, you can click on it, it'll give you a value if you go into calculate, and what you see is that y is very, very, very close to 1 when eta is 32. So that is something that is confirmed by what we got up here, all right? And so, whoops. So we'll make our picture. All right. And so what'll happen is you can see the graph, and this right here is the sequence S sub n, where S sub n is equal to 2 to the n minus 1 over 2 to the n, and we're assuming S sub n is ordered. You don't have to have these sets ordered. And so here, do you see that we have something which is monotonic, right? Because it's non-decreasing, right? So S sub n is monotonic, non-decreasing in this case. Now, bounded above at approximately 1, and bounded below at, the first one is what, 1/2, I think, right? At 1/2. And so what we learned from the last section is so that means that our sequence is bounded. So let's take a look at these requirements here. So we learned actually in 9.1 at the end, sorry, I'm skipping around, but if a sequence is bounded and monotonic, it converges. And we did find that this sequence converges. It just happens to be a sequence of partial sums. Pretty cool, huh? Okay. All right, so now let's go over to here. We're going to look at telescoping series, right? So a telescoping series is of the form, the summation from n equals 1 to infinity of b sub n minus b n plus 1, which will be b1 plus b2 minus b2 plus b2 minus b3 plus, do you see how the trend? B3 minus B4. So they end up at some point zeroing out, right? Successive terms zero out the ones before. And so this would keep going on as you got to the b sub n plus first term, or b to the nth term, b sub n, and then minus b sub n plus 1, and plus dot, dot, dot. So as you can see, what happens is these B2s zero out, the B3s zero out, etc. And everything past a certain first number of terms will zero out. So note that, like I said, B sub 2 is canceled by the second term, b sub 3 is canceled by the third term, and so on. So it doesn't always happen that quickly, but let's check it out, what we have going on. So here we go. A lot of times partial fraction decomposition is required, so I did leave some space for this one. So here we have 1 over quantity n times n plus 2. So we don't really know what to do with that right now. So let's go ahead and do some partial fraction decomposition to see if it turns out to be a telescoping series. So let's do this. We have 1 over n times n plus 2 equals a1 over n plus a2 over n plus 2. So quickly we'll have 1 equals a1 times n plus 2 plus a2 times n all over, and this is 1 over, n times n plus 2. And now we've got n times n plus 2 on both expressions, which means we just need to equate our numerators. So we have, let's see, a1 plus a2. Both of those are paired with an n, and then we have plus 2 times a1. And so we need a 0 times n to have an n term. And then equating coefficients, right? We will have a1 plus a2 is 0, and then the constant term equates to 2 times a1. So, working out that little system, we can find from the second one that a1 is 1/2, and if that's the case, then a2 must be equal to negative 1/2 to make that first equation true, which means we will get, if we factor out a 1/2, well, I'll do that later, we'll get 1/2 over n minus 1/2 over n plus 2 is the partial fraction decomposition of 1 over n times n plus 2. So I'm going to factor out that 1/2. So if we rewrite this series as 1/2 times the summation as n goes from 1 to infinity, we will have 1 over n minus 1 over n plus 2. Now let's go ahead and find some of those terms. So this will be equal to 1/2. When n is 1, I'll get 1 over 1 is 1 minus 1 over 1 plus 2 would give me 1/3. And then now if I plug in 2 for n, I'll get 1/2 minus 1/4. And then plugging in 3 for n, I'll get 1/3. So the trend is starting, minus 1/5. I'll go one more. I'll plug in 4. I'll get 1/4 minus 1/6. And now look what happens. The 1/3 zeroes out. The 1/4 zeroes out. The 5th, the 6th, they're all going to zero out. And so at the end of the day, we will get 1/2 times 1 plus 1/2. Well, 1 plus 1/2 is 3/2, so we'll end up with 3/4. Pretty cool, huh? You can find this infinite sum, right? But we have to make sure, everything else is going to zero out. So you really want to add the limit as n approaches infinity of your n plus first term. Okay? So what will happen is, and we could really distribute the 1/2 to both, okay, just to be proper. So we'd have 3/4 from the first bit plus 1/2 times the limit as n approaches infinity of, well, the n plus first term would be 1 over n plus 1, I'm just plugging in n plus 1 wherever there's an n, minus 1 over, well, this one I'll get 1 over n plus 1, and then plus 2. So that would be n plus 3. Well, as n gets very, very large, that will go to 0. And 1/2 times 0 is 0. So we have found that our infinite sum goes to 3/4. And this is a telescoping series. Pretty cool, huh? I think it's really pretty powerful that you can find, so this whole thing here. I shouldn't use that color probably, since I did that on the partial fraction stuff. This whole limit here was 0. Okay, so anyway, this is an example of a telescoping series, and it's a nice, powerful thing that we can take something that is infinite and we can find its infinite sum, right? Okay. Now, this next one's a little bit of a different animal, right? It's not telescoping. It's actually considered to be a harmonic series. So I decided to go ahead and give you the math proof for it, and then we will show you what the sequence of partial sums looks like, okay? So here we go. Show that the series from n equals 1 to infinity of 1 over n diverges. So we're going to suppose that the series converges. So this is a proof by contradiction with some sum s. Well, then, if that were true, S would equal to, so we'll just start getting some terms, right? The first one would be 1 over 1, which is 1, plus a half, plus a third, plus 1/4, plus 1/5, plus 1/6. Don't worry, I won't go forever. Plus 1/7, plus 1/8, plus ... And what'll happen here is that let's look at what we have there. And now what we're going to do is we're going to group. So if we group two terms at a time. So I'm not changing anything, just grouping them. Now, here is where the really cool, so easy, it's hard thing comes in. So now we're going to say what we have here is greater, okay, than a half plus a half. Would you agree? Cool. And then for the second one, we're going to take that second part of the grouping and just say a fourth plus a fourth plus a sixth plus a sixth. As the denominator gets larger, the fraction decreases, right? So basically, these are all smaller than the line before. So then, what is this equal to? So this inequality happens to be equal to. So the first grouping is 1 plus a quarter plus a quarter is a half. A 6 plus a 6 is a third. An eighth plus an eighth is a quarter. But that equals. So that is saying that S would be greater than all this. But isn't that what S equaled? So we have found a contradiction, right? Because why? S is not greater than S, right? So, hence, S equal to the summation from n equals 1 to infinity of 1 over n diverges. Pretty cool little proof, right? I like that one. Easy to follow, easy to see. Okay, so next up are geometric series. Or the geometric series. So a theorem that we have for this one is a geometric series with ratio R converges to the sum. So it's very powerful. Note that n starts at 0, goes on infinitely, and we have a times r to the n, and it equals a over 1 minus r. but only when 0 is less than absolute R, which in turn is less than 1. So I always kind of think of this as a proper fraction in between 0, so you have a fraction in between 0 and 1. Otherwise, for absolute R greater than or equal to 1, this series diverges. So let's check it out, how it works. Determine if the given geometric series converges or diverges. Well, if we identify each of our components here, A is just 1, right? There's a coefficient of 1. And then R is equal to 2/5, right? Because that's everything that's being raised to the n. So, is 0 less than absolute 2/5 less than 1? Yes, right? Because 2/5, absolute 2/5 is just 2/5. And so, by definition, it will converge, okay? So it actually only asked us to find out about convergence, right? So we'll say for our conclusion that yes, the summation from n equals 0 to infinity of 2/5 to the n is a convergent geometric series. Now, if you're only asked if something converges or not, then you don't have to worry if your index starts at 1. We're looking at, behavior as your n goes to infinity. So if you're only worried about convergence or divergence, don't worry if the behavior doesn't happen for a little while. So this is our official answer. All of the work is part of the answer because this is how we were showing what was going on, right? Now, this one, it's a little bit more important to look at the indices because the first one starts at 0, but the second one starts at 1, right? So I think that it might be useful to sort of play around with that a bit, right? So this series will equal to, or this, combination of series is going to equal to, the first one is fine on its own, n is 0 to infinity of 5/6 to the n. Now the second one, I'll do in a different color, is going to be equivalent to, we want it to be the summation as n goes from 0 to infinity of 1/3 to the n. But in order for that to be true, right, we're going to have to subtract the 0th term. So we're going to have to subtract, this isn't part of the summation, the 1/3 to the 0 because we will have added too much. So let's see what we've got going on. So now we have, this will equal 2. So for our first one, again, on both of them, really the A is 1. So the infinite sum, remember, will be, I'm looking at A over 1 minus R. So 1 over 1 minus 5/6 for our first one. And then minus, so for the first part, we will have 1 over 1 minus 1/3. And then minus a minus is a plus, and 1/3 to the 0 is 1. Cool so far? So now, finishing it up, we'll have 1/1/6 minus 1/2 plus 1, which is 6 minus 3/2 plus 1. And what's that going to be? 7 minus 3/2. And then getting a common denominator, that would be 14 minus 3/2, which gives us 11/2. Good so far? Awesome, awesome. So there, we didn't need to show that it converged because we found out that it converged as we went through. Notice that our 1 was 5, 6, which is definitely between 0 and 1, non-inclusive. Our 2 was 1/3, which is the same between 0 and 1. Cool, cool? All right, so let's continue. Now, this is a really fun application. Express the number as a ratio of integers. So this really, if we wrote it out, would be 0.46 plus 0.0046. The 46 is the repeating part. Plus 0.000046. And you'd keep going like that, right? And then this in turn is going to be equal to, if I factored out a 0.46, I would have my common ratio, which, I mean, one easy way to find your common ratio is to divide one of the terms after by the term before. Right. And so that would be equivalent to which 0.46 over 46, right? Which ends up being 0.01. Cool, cool. And so we would have 0.01 to the 0, right? Because that's 1. And then plus 0.01 to the 1, which would give us the second term, plus 0.01 squared plus ... And then continuing, we have our ratio, we have our A. So this would be the summation from n equals 0 to infinity of 0.46 times 0.01 raised to the n. Well, 0.01 is between 0 and 1, non-inclusive, and so this will give us A, which is 0.46, over 1 minus R, which is 0.01, which is 0.46 over 0.99, which is 46/99. Pretty cool, huh? It's really kind of trippy if you do this problem and you do like 0.99 repeating. All right, so anyway, the next thing that we're looking at is the nth term test for divergence. All right, so properties of infinite series. We need these for our nth term test and just for some good stuff here. All right, so let the summation from n equals 1 to infinity of a sub n and the summation of n equal 1 to infinity of b sub n be convergent series. And let capital A and B and then lowercase c be real numbers. So if the summation from n equals 1 to infinity of a sub n equals capital A, and the summation of n equals 1 to infinity of b sub n equals capital B, then the following series converge to the indicated sums. So if you have the summation of a constant times a sequence, you can take the constant out and then it's multiplied to the sum of the series. And then if you are adding two sequences within a summation, that's equal to the sum of their sums. And again, the difference, if you have a difference of sequences in the summation, you'll have the difference of their infinite sums. Now, the limit of the nth term of a convergent series. So if you think about it, at some point, your sequence inside the series would have to be going to 0, wouldn't it? For it to not be adding on anymore to the sum, all right? And that's what this says. This says if the summation, and it just goes one direction, it's an if then, so the opposite is not true. So if n equals 1 to infinity, the sum from 1 to infinity of a sub n converges, then it turns out that the limit as n approaches infinity of a sub n has to be 0. At some point, you're not adding any more in, all right? So the proof for this is kind of cool. What we're given is that the sum converges. So since the summation as n goes from 1 to infinity of a sub n converges, right? Well, then the summation as n goes from 1 to infinity of a sub n will equal to the limit as n approaches infinity of the nth partial sum, and that will just be sum L, where L belongs to the real numbers, okay? Then we will have S sub n will have to be, just like that problem we did above, it'll have to be S sub n minus 1 plus your nth term. Would you agree to that? Cool. So now let's find the limit of each side. So the limit, because that's, what we want to show is a limit, right? As n approaches infinity of S sub n would be equal to the limit as n approaches infinity of S sub n minus 1, the n minus first partial sum, and then plus a sub n, the nth term of the sequence inside the series. So we know that the left-hand side is L. That's going to equal to the limit as n approaches infinity of S sub n minus 1 plus the limit as n approaches infinity of a sub n. So now we have that in there, which is nice. Well, if the limit as n approaches infinity of S sub n, which we found right above, is L, don't you think the limit as n approaches infinity of S sub n minus 1, wouldn't that also be L? And then we'd still have the limit as n approaches infinity of a sub n. But then when you subtract L from both sides, we will get 0 is equal to the limit as n approaches infinity of a sub n, which we wanted to show. Groovy? Okay. so next up, we've got the nth term test for divergence. Okay, so notice it used to just be called the nth term test, but then people were using it wrong. They were using it to show convergence. So they actually changed the name in this text to the nth term test for divergence. It will only show divergence. So if the limit as n approaches infinity of a sub n, so the sequence inside the series, is not equal to 0, then the summation from n equals 1 to infinity of a sub n diverges. So it only will show divergence, all right? So you see something like this, really almost anything, try the nth term test for divergence first. If you get a non-zero result, you're done. And you can go home. You can go have a margarita or something. All right, so let's take a look. Our test that we're gonna use, we're gonna see if it works, if it diverges by our nth term test for divergence. So let's see, what is the limit as n approaches infinity of arctangent at n? I'm guessing your Calc 2 teacher probably told you to memorize this. Basically, you'll get pi over 2, and pi over 2 is not equal to 0. If you need to graph it, go ahead and graph it, but you will get pi over 2. And pi over 2 is not equal to 0, so therefore, in conclusion, the summation from n equals 1 to infinity of arctangent at n diverges by the nth term test, and yes, you need to write this, for divergence. We're done. So both parts, I won't just box one thing, both parts were part of the answer. So now let's take a look at part B. We've got -3 raised to the n minus 1 over 4 to the n, right? So with that one, if we take I think what we might want to do is take a look at this as a geometric series. So if we do a little bit of magical rewriting here, and we write this as the summation as n goes from 1 to infinity of, this would be -3 to the n times -3 to the -1 over 4 to the n, which is the summation as n goes from 1 to infinity of -3/4 to the n times -1/3. So -1/3 would be our A. Okay, so here we don't need to find the sum, so we don't need to worry about changing the limits of integration. What we are interested in is R is equal to -3/4. So would you agree that 0 is less than absolute -3/4, which is less than 1? So the summation from n equals 1 to infinity, I'll write it as our original of -3 to the n minus 1 over 4 to the n, is a convergent geometric series. So that one converges. They didn't tell us to find what it converged to, so don't worry about it. Okay, so part C. Here we go. A little bit of heavy lifting on our limit work, right? So here, and I'm looking at it, I'm seeing it's not a geometric series. In a geometric series, your base is known, it's your power that's unknown. And here we've got an n, 1 over n inside there. So here we go. We're going to look at the limit as n approaches infinity of 1 plus 1 over n to the n. Now, it's not very illuminating, right? Because we'd end up getting 1 to the infinity, which is an indeterminate form, all right? So what we will do here is we will rewrite this as the limit as n approaches infinity of. Now it gets weird because we're going to write it as e raised to the natural log of 1 plus 1 over n to the n. So we just messed it up a little, but that equals what we started with. And the reason we did that is so we could use that power rule for logarithms, right? This is going to be the limit as n approaches infinity of e raised to the n times natural log of 1 plus 1 over n. Cool so far? Okay. Now, we still don't have it in a form where we can use L'Hopital's rule. All right, remember with L'Hopital's rule, you either need 0 over 0 or infinity over infinity in some form. And this, if we directly substituted, would give us infinity times 0. Still not a form we want. So with a little bit more algebra, we will have natural log of 1 plus 1 over n over 1 over n. So do you see that I just changed this n up here? And that's, of course, all raised to the e. So that's all in the exponent of the e. And now let's take that limit inside there. So this is going to be e raised to the limit as n approaches infinity of all this stuff, okay? So we'll have our natural log of 1 plus 1 over n over 1 over n. And this is a result where if we directly substituted, we would get 0 over 0. And so L'Hopital's rule applies. So since L'Hopital's rule applies, because you'd get natural log 1 in the numerator, and you would get, which is 0, and then you would get 1 over infinity, which is 0. That's why we get 0 over 0. And L'Hopital's rule basically says, hey, if you get 0 over 0 or plus or minus infinity over plus or minus infinity, the limit of the derivative of your expression is the same as the limit of that expression. So we'll differentiate. We'll get e raised to the limit as n approaches infinity of. So the natural log derivative is going to give us what? Negative 1 over n squared over 1 plus 1 over n. So it's like u prime over u, right? And then I'm just going to write it as divided by, because I don't have room below, divided by negative 1 over n squared, which is the derivative of the denominator. Now when I simplify this, I'll get e raised to the limit as n approaches infinity of. negative 1 over n squared over 1 plus 1 over n, and then times negative n squared. Well, that divides out the numerator. So in the numerator, we'll have e raised to the limit as n approaches infinity of 1 over 1 plus 1 over n. So we'll end up getting e, that whole limit is going to end up being 1, which is just e, which is cool, but that is also not equal to 0, right? And so we can conclude that the summation is n goes from 1 to infinity of 1 plus 1 over n to the n diverges by the nth term test for divergence. All right, excellent. All right, so now an application. So a ball is dropped from a height of 16 feet. So let's say this is where the ball is dropped from, some platform or something. And then you have this little person. They're holding the ball down here. And this ball is right at this platform, which is 16 feet up. So now what'll happen basically is that I'm going to go to a dotted line. So it'll drop, right? And let's say that's 16 feet, right? And then it's going to bounce. And it says that it bounces up 0.81 times h feet. So the first time it bounces, it's going to be, about 80%, and then about 80% of that, and etc. Yes, I'm not an artist, ... And it keeps going until it stops bouncing. And so now put it back to regular line. Okay, so from here to here is your 16 feet, all right? So now what happens is you have your 16 feet one time, right? So we want to know the whole distance that the ball ends up going. So our distance, right, will be equal to 16 as it drops down the first time. And then it travels up 16 times 0.81. And then it goes down 16 times 0.81. You see that? And that's to the 1, right? That's going to be our R. And then it would go 16 times 0.81 squared plus 16 times 0.81 squared, right? And it would go on and on with that behavior. So if you think about it, you have 16 plus 2 times 16 times 0.81 to the 1 plus 2 times 16, 0.81 squared, plus 2 times 16, 0.81 cubed, plus dot, dot, dot. So now working with this, right, we would have 16, factoring out a 16, times 1 plus 2 times 0.81 to the 1, plus 2 times 0.81 squared, plus 2 times 0.81 cubed, plus dot, dot, dot. So then, 16 times 1 is just going to be the 16, because everything else has that 2. Do you see that? And then we're going to have plus. So that's plus. And then I'm going to do a summation for the rest. So plus the summation from n equals 1 to infinity of 2 times 0.81 to the n. Now I need to subtract out the term where n is 0. So when n is 0, right, you'd have 2 times 0.81 to the 0, which is just 2, correct? So, and we still have, the 16 going on. Good so far? So we're going to have, we'll have 16. We need to subtract out 16 times 2 because that's the 2 and it's got a 16 multiplier. And then we'll have plus 16 times the summation, n is 0 to infinity of 2 times 0.81 to the n. Good so far? So now 16 times 2 is 32, so we'll end up with negative 16 plus 16, and then we can do our sum. So our a is 2. 1 minus 0.81, so our 1 minus r. So that will be negative 16 plus 32 over 0.19. And then when you compute that one, so we can get a regular number here. That would be negative 16 plus 32 divided by 0.19, and that's going to be approximately 152.42 feet. Cool so far? So let's make sure we answered the question. All right, the total distance traveled by the ball. Approximately 152.42 feet. Cool, cool? All right, so that's all we have for today. I hope you have a wonderful morning, afternoon, or evening whenever you are watching this show. Hey, if you like what I'm doing, click that share button, subscribe button, and like button. Bye. See you next time.